up to now. In every 3 years means the number of transistors doubled in per square inch is happening in every 3 years. So this is the Moore's law observation. So what are the benefits from this Moore's law? So the benefits are, one is Moore's law says that if more transistors are increased, there is an increase in opportunities for exploiting parallelism in the instruction level. That means what? Suppose if I have a program, or if I have a task T which requires suppose 10 seconds time. Okay. So if I execute this entire task with only one processor, and if I give this task as an input to this, then it takes 10 seconds time. Okay. But instead of that, if I have two processors, suppose this is P1 and this is P2. If I have two processors, then this entire task is divided into two parts. One is given to processor P1, another part T1 is given to processor P1 and T2 is given to P2. Then this processor can execute this in 5 seconds. It can execute in 5 seconds, but they are not dependent on each one, so they are separated to each one, so the entire task can be executed in 5 seconds only. So if I increase one more processor, suppose another processor is there, it is possible to divide this, the entire task into three parts: T1, T2, T3, and the T3 can be given to another processor. So P1 may take 5 seconds, P2 may take 2 seconds, another may take 1 second. I don't know. So it can change. So that is the meaning. Says that if more transistors are there, then there is a exploitation of parallelism in the instruction level, so that the pipelining parallelism can be happen, pipelining can be happen, or the superscalar can be happen. So that is possible with the help of, means the very long instruction word, instead of only 8-bit instructions, it can execute the 12-bit instruction by increasing the processor, or 16-bit instructions. So that we call the word. And very large word means 32-bit instructions can also be, or 64-bit instructions can also be executed. So this we call the very large. The instructions can be executed by increasing the number of transistors, right? So based on, by increasing this Moore's transactions, based on that, the various methods, the instruction level, the parallelism happen. One of them is your SIMD and your vector processing. That means single SIMD is single instruction multiple data. That means suppose if I write a program A plus B is a program, then if I define where A is set of 1, 2, 3, and where B is a set of your 4, 5, and 6, suppose, then this same instruction, only single instruction, that is plus, can be written as 1 plus 4 one time, your 1 plus 5 another time, 1 plus 6 at that time, 2 plus 4 at that time, 2 plus 5 at that time. That means what? Everywhere you are finding only the addition operation, single instruction, but every time data is changed, multiple data. So that is possible. Single instruction, multiple data, or the vector processing is possible by increasing the Moore's law, and that is the observation of your, the benefit of your Moore's law. Another says that the general path of scaling. The general path of scaling means what? To execute these instructions, to execute these instructions like A plus B, the wider instruction issues, longer pipeline is possible. So if there are more speculations, is possible with the general path of scaling. Means if you increase the number of paths, or if you are able to supply the data for various pipelines, then it is possible to execute them parallelly. So that is more speculation is possible, and more and the larger registers and cache is possible by increasing the number of transistors. Another benefit or another the observation and benefit says of more that increase in circuit density, that means number of transistors in a small square inch, or your inch square area in this die. If number of transistors are going to be increased in small, then the density of your circuit is increased. When density of circuit is increased, its frequency is going to be increased. When frequency increase, its performance will be increased. So as density increase, its frequency increase. Frequency increase means the performance will be increased. And then finally, another observation that the benefit is it is transparent to the user. An easy job of getting better performance. So buying faster processors, that is the higher frequency. So every user, they try to get better performance performing machines than the the harder ones. So that is the another benefit part. Then comes to from this Moore's law, there is one more author who studied on this Moore's law and find out some flaws, some other ideas, and try to incorporate with the Moore's law. Whose that author name we call the Robert Denard. He is a IBM fellow, whereas your Moore's law is co-founder of your Intel processor. So what this Dennard scaling is saying, as transistors are get smaller, their power density stay constant. That means the power is not going to given to any individual transistor. Power supply is provided to the die of it is in the in inch square area. If you increase the number of transistors on this die, the power will be constant, but the density of the transistors are going to be increased in this case. So I say the transistor, as if you are going to accommodate more, then the transistor size will be reduced in terms of. So as says, as the transistors get smaller, their power density stays constant, so that power use stays in proportion with the area. So that is in terms of both voltage and the current scale with the length. So here, what the exactly means. It says that the current and voltage, the power density, the power density will be stay constant with the help of your current and the voltage part. So this is what the Dennard scaling observation. It is also an observation. It is not an equation or mathematical equation power. So what it says, what Dennard scaling means for each new generation processors, we can double the transistor count every 2 years, as said Moore's law. But along with that, we can double the frequency without extract power uses. That is his observation, which is added to the Moore's law. So therefore, we can more than double the performance for each new generation processors. So this is why the computer industry was so successful in the decade from 80s and 90s. So the performance gain in guaranteed and is free. That means no extra power is required. But unfortunately, the Dennard scaling started to fail around in the year 2014 onwards. Reason is the frequency growth stopped, and the growth of single core processor performances has significantly slowed down. Then it becomes the core to duo or duo to core that was evaluated the later years. Right? So you can see his observation. This is the diagram which is taken from his from the paper which is developed by these authors. It says from 1975, from those decades, as per Moore's law, it says that the number of transistors have doubled in every year, and it reached to up to 2013. In that year it is doubled, and after that in every 3 years it start increasing the number of transistors in thousands. And here, along with these transistors, Dennard scaling is talking about the frequency. So the frequency is also gradually increased or doubled in every 2 years. But when it reached to the mid of 2004, from there it start, decreasing. The frequency is fail point. So this is the stall of the CPU frequencies part in terms of the registers. Okay, so then the computer architecture after the post or after the Dennard scaling era, the parallel processors came into the market. So instead of doubling the frequency, we doubled the number of cores that can help, but no long-term solution it is. Okay, then the specialized processors came into picture. Those specialized processors, one is very important, very the famous one is your graphic processing units, GPU, for the general purpose data processing, that is for scientific and machine learning purpose these processors are using. Another one is application specific integrated circuits. In this application specific integrated circuit processor, that is used for your machine learning processors, and hopefully the graphene or the quantum computing can save us in coming days by increasing this processor's power. So dealing with the complexity observations, sorry, abstractions. So abstractions means in computer architecture, it says that the computer architecture is a layered architecture. It says instruction set architecture is layered, then the micro architecture design, then the system architecture design, that is the abstraction. So as an architect, the main job is to deal with the trade-offs. That is, the performance should be high, they should reduce the power consumption, and die size should be very less and increase the number of transistors in that die size. Complexity should be very simple, and it must given to the various applications. As we said, application support oriented. Their functionality, compatibility, and reliability is the dealing with this complexity part, right? And another one is the technology trends and their applications. So how do we deal with all of these to make real trade-offs is most important. That is, the abstractions allow this to happen. This all happens with the help of your abstraction. So this abstraction is the layered the design, which allows us to focus on the design and optimization of the layer at a time. So that is instruction set, microarchitecture, system architectures are three abstraction layers. At every layer, if you try to improve or optimize, then automatically its performance will be increased. And at functional, at micro architecture level, if your improvement is happening, means power consumption will be reduced, die size will be reduced, complexity will be reduced, and and its application area functionality will be increased. So the CPU and memory are two abstraction layers to deal with the complexities. The another one, design metrics in terms of the performance. First one is abstraction, another one is performance. So performance means reduce the response time or the execution time. So the time between start and the completion of an event known as your response time at the execution time, and it must increase the, so the total amount of work in the given amount of time is called as the total amount or the throughput we call must be increased. The execution time is the reciprocal of the performance, that is x is 8 times faster than your y. That means you can say n is the execution time of y divided by the execution time of your x. So n is compared with the y and the x part. So that is the wall clock time and your CPU time. That is not the input output one that gives the performance metrics, right? And then the another design metric is cost. It must reduce the cost. So the goal is to reduce the manufacturer cost, and by following the Moore's law, which also helps here as doubling the transistors, that does not require more raw materials, but however, the smaller transistors make it harder for a quality control. Then another design metric is availability. So availability means the fractions of time, the fraction of the time a system is available. And for servers, it may be important as performance, but mean time between failure is more important for the availability. Mean time between failure, whether your system will be available or not. So that is the period that a system is usable, typically around 500,000 hours per a PC hard drive. That gives the availability of any PCs. And typical lifetime of a central processing unit is 10 years. After that, it slowly become its availability becomes slow down. So mean time to repair, MTRR, that is recovery time from a failure, that should approach zero for a big server, or redundancy is required. And another metric is power dissipation. So in power dissipation, all understand why energy is important for embedded the central processing unit. So that's all. The high-end servers, they require 130 to 170 watts, and high-end desktops, they require 70 to 100 watts, and high-end laptops, they require 30 watts of power dissipation, and the battery optimized laptops, they use the 3 to 4 watts, and the embedded CPUs, they use the 5 to 1 watt, and the DSP use the the 100 microwatts. So the for microcontrollers, the power dissipation, it is approximately like 10 microwatts. And okay, so with this, I would like to stop the session. So this is all about the computer architecture and the general idea of computer architecture.